So now we're going to talk about, in this next two lectures, two key innovations for training neural networks. One is called the backpropagation algorithm. So backprop is a commonly used term, which basically just simply means chain rule, and we'll see that in a moment. And the second is stochastic gradient descent, or variants thereof. So stochastic gradient descent was the first version of how to do gradient descent at sort of some large scale that we have available to us. So those are the two algorithms we want to talk about because they were absolutely critical and actually driving the success of machine learning. In other words, being able to take these neural network structures and actually find the parameters for them, which means you have to do an optimization at massive scale. And neural networks now allow us to do this. The infrastructure is there. So the advances in optimization, the advances in compute, the advances in theory have allowed us now to be able to leverage the power of deep neural networks. And this is only something that we've been able to do over the last 10, 15 years, where we actually had all of these things come together, allowing us to actually even be able to compute these objects that we're talking about now available to us in neural networks. So again, this is all around machine learning using the neural networks, right? We've already talked about non-neural network methods. And so these two lectures are going to really focus in on, in some sense, the basic building blocks of how all of this has been driving forward and how neural networks themselves were enabled by backprop stochastic gradient descent to be able to perform now at levels that are beyond what any of the other, typically beyond any of the other non-machine learning methods, non-neural network machine learning methods can do, especially with large data. So the goal of this lecture is to talk about backpropagation, backprop, or really it's just chain rule, okay? So chain rule is one of the things we learned in the first few weeks of calculus. And so that's all this is, right? Which is if you're going to differentiate in a function, you have to make sure to do your chain rule to get the actual function itself separated out to take the derivative of itself, okay? So let's walk through how this might work. And I'm going to give it as a very simple example. I'm going to give you, this is my neural network example I'm going to give you. It's going to go from an input, it's going to have one hidden layer, to an output. All one dimensional. This is about as simple, actually, this is the simplest neural network I think you can make with any kind of hidden layers. And so my input is x, and x gets mapped through some activation function f with a parameter a, let's say, to the hidden state variable z. So I'm going to assume that this activation function is one parameter. And then from z, I map to the target output y through some activation function g, which takes me from z parameterized by b. So I have a parameter a, and I have a parameter b that I have to determine, which would take me from the input to the target, which is the output, okay? Now, right away, you see there's a compositional structure here, right? So x goes to z, z goes to y, and so you have this functional form at the output, which is y is a function of g, which is a function of f, f is a function of a, g is a function of b. So this is the compositional form of the function we need to find, and our objective is to determine what should a be and what should b be, okay? And so we're going to determine this by chain rule or backpropagation. So here's, first of all, what we've got to decide. First, we have to pick activation functions. In other words, typically we go from one layer to the next, we pick some activation functions. We want them to be nonlinear. The reason we want them to be nonlinear, because if you chain together a bunch of linear layers, that can all be equivalent to just simply a matrix multiply. And so you don't need all this machinery. The nonlinearity itself is critical in the curve fitting process. Second, you want a very simple function to differentiate. And so I'm giving you here some very simple functions that are standardly used as activation functions in neural network training. You have a linear layer, which is actually not what we want, because if you have just a linear layer, often people use a linear layer at the output layer, so that's just x here. And in fact, oftentimes in a deep neural network, you would have multiple layers with different activation functions. Often people put a linear layer at the very end, okay? You have a binary step. here it is. It's 0 if x is less than 0, and 1 if it's bigger than 0. You have this logistic map, or logistic soft step, which is something that does something like this, and it goes up and straight over. That's also what the tanh does. Or you have here, which is commonly used, it's called ReLU, rectified linear units, which is 0 if x is below 0, and x if it's above 0. All of these functions, you can just compute the derivative, okay? And in fact, they're kind of trivial. Like this one here, f of x here, you know, the derivative on the left is 0, the derivative on the right is 1. Okay? And typically we're going to throw a parameter in front of this, so it's f of a of x, so the derivative either be 0 and the derivative be not 1, but a. Okay? So the key here is when you pick one of these activation functions, you should be able to just write down the derivative of it. And that's going to be an important piece of this, because you're going to basically have to compute derivatives at scale. So if you already know what they are, that's what you're going to be using in the backprop. All right, so let's go back to that simple example then. Given an activation function, we say my output y, right? There was a function g which mapped z, which was the hidden layer, with a parameter b. But z itself was the function f, which mapped x over to the hidden layer with the parameter a. So I have two parameters here. I have a compositional structure. So now what I'm going to do with this is I'm going to start thinking about, this is my target output. So if I put in x, I'm going to get an approximation to y. Of course. So let's call it y tilde. And there's the real y, and there's my target. So my target is y, and I have my approximation y tilde, and I like to make those as small as possible across the data set. So the way you would structure this objective function is like this. E here is the error, and I've written this down as a sort of a root mean square type error, which is, you'll see why I have the 1/2 here, because I'm going to have to take the derivative of this. So I put the 1/2 here to take care of, when I take the derivative, take care of that 2 that comes down. So it's 1/2 y naught minus y. So y naught, let's call it my target. That's the actual value of what I'm trying to hit. Y is my approximation. Okay? And I'm going to try to minimize this. So how do I pick A and B so that this thing here is minimized? Okay? Well, if that's the case, what do I have to do to this? If I want to minimize the error, I want to take the derivative of this error with respect to what? Well, there's two parameters, A and B. That's what I'm trying to find. So you take the derivative of this with respect to A, set it to 0. Take the derivative of this with respect to B, set it to 0. So that's the concept here in terms of mapping these things forward. Oops, I think I missed one. So, sorry. Yeah, here we go, and there we go. So here is the backprop. Yeah. Backprop chain rule. Okay, here we go. So now let's go ahead and take this error calculation, and let's do the following. So now I take the error that I have there and take the derivative with respect to A. Well, the 2 comes down. I get minus y naught minus y1, and then I have dy dd, dz dA. This is where the chain rule comes in. Remember, I'm taking the derivative with respect to A, but A is buried all the way in the z. So to get to it, I have to first take the derivative of y with respect to z, but then z with respect to A, and I want to set this equal to 0. So this is it right there. That's the chain rule we're talking about. So that's what they call backprop. So if I take the derivative of the error here, it goes back propagates through the neural network to get to the parameter you're trying to optimize against, which in this case is A. Okay, this is all screwed up. Boom. Okay. So this is then going to give us a gradient descent step. There we go. So the gradient descent step then is you can do the same thing for B. And so then what you're going to do is say, and by the way, remember, these are typically, all these activation functions are nonlinear. So like, even though we're trying to set the derivative equal to 0, what we're really trying to do is just get a gradient direction to walk downhill. These are nonlinear functions that we're optimizing over. So what we want to do is when we compute that derivative, it's giving us the derivative or the direction of downhill. So another way to think about it is I start off with some initial values of A and B. Those are the parameters of the neural network given my activation functions. And I compute the error. And what I do is say, okay, well, I want to walk downhill. And so what you do is say my new value of A is my old value of A plus a learning rate, the derivative of V with respect to A. Same thing with the B. I'm going to update the B value. So I started off some initial guess maybe. The new value of B is the old value of V plus learning rate delta. And the way I walk it downhill is by computing this gradient. So what you're doing here is finding the downhill direction, taking a step of size delta in that direction, how I have now a new value of A and B. And then I do it again and again and again until I converge, or at least get close to some kind of convergence or stopping criteria. That's it. So you're basically structuring this up so that backpropagation gives you the necessary pieces to do the gradient descent. Remember, it's a partnership between these. You're going to do gradient descent at scale, but you've got to figure out how to go downhill, and you figure out how to go downhill by using the backprop algorithm to be able to compute these things explicitly. Okay, so in fact, let's do that. Let's compute these things explicitly. So let's consider the following: linear activation functions. So the linear activation functions, we're going to take the f and g. Remember, the f goes from the input to the hidden layer. G goes from the hidden layer to the output. Each has a parameter, a or b. Right now I'm just calling them alpha. So let's suppose these things are just simply a linear activation function, alpha c. Okay? So that's what I have in each layer. So what I want to do is, this is more of an example just to show you how you would compute these things, is you would say like, okay, so my transfer functions then, if I go back to the original coordinates, is my z, which is my hidden layer, is just the constant a times x. That's how I got from x to z. And then when I go from z to y, it's b times z. So these are the linear transfer functions that I have available to me. So now I have these explicit representations of z as a function of x and y as a function of z. Okay? And so now I can compute gradient directions by doing the following. Here we go. So first of all, let's start with dEDA. In other words, how do I go downhill in the air with respect to A? Okay? Well, you take the derivative of the error, which you brought down the 2, cancels negative half. You get y naught minus y. You get dy dz, dz dA. Well, you can actually compute dy dz explicitly. It's actually b. And you can compute dz dA explicitly, which is x. So there you go. This is the gradient direction. Notice I just have to know this once. So all of this architecture for computing these is built into frameworks like Torch and JAX. All of it's there. So depending upon, you pick your activation function, it's already pre-computed all of these for you, right? Or at least the expression you need to evaluate. So that's maybe the more correct way to say it. It has pre-computed this expression for you, given an activation function in whatever layer you're on. dEDB, again, same thing. You take the derivative here, but now you can just go one layer in, dy dB, and then you can compute this out. Here it is, y naught minus y times z, but what's z again? AX. So you see here, what we have is an evaluation of the downhill direction already explicitly computed. Okay? And this becomes the basis for using this in a gradient descent algorithm, and the backpropagation was what allows you to do it. The backpropagation was says, okay, I got to take all these derivatives, which means I've got to walk backwards through the neural network, take the derivatives back to all the parameters, and give you some nice representations. Here's the nice representations. Okay? So again, all of this is packaged up. You don't have to write code for this. Thank goodness, right? Torch, TensorFlow, JAX, all of these basically package this up so we don't have to think about this so much, but this is what's going on under the hood. Okay. More broadly, back up one. What we have is, if we have additional layers, you just simply get something like this. So you can have a bunch of hidden layers, but it's the same thing, just chain rule. Remember, A is in the first layer, so if I take the error, which is all the way at the output with respect to A, I have to go back through all the layers. So you take the derivative, dy dz of m, dz m dm minus 1, all the way to dy dz, d2, dz1, dz1, dA. So this is the backprop propagating all the way through, which is just your chain rule calculation that you would have available to you. Okay. All right, there's that. All right. So ultimately what this results in for the backpropagation is the structure of the gradient descent. So if I collect all my weights in a vector W, then my update of the vector W is I have wherever I am now. In other words, if I started off with some initial weights, and these weights are typically randomized, are randomized values. So I start off with W0, I'd compute the gradient direction, which the backpropagation allows me to write down formulas for this. And I take a step of size delta. That's called the learning rate. So I take a step in the downhill direction with size delta, and I have new values of weights. And I just keep doing this. It's an iterative procedure and walk downhill. And every time I take a step, I compute the gradient there, take a step downhill, compute the gradient, take a step downhill. And then you keep going until some convergence or stopping criteria that might be achieved for this. So this is sort of the foundations of training a neural network, this architecture, which is really simple ideas from like the first couple weeks of calculus. And I really want to emphasize this, right? In many ways, neural networks just are relying on the things we learned very early on in calculus, right? This is just curve fitting and gradient descent. These things are like very simple ideas that we learned early on in our mathematical training. And we're just doing this at just massive scale. But really fundamentally, we're not really doing anything that new, right? This is a curve fit. It's just that it's a very fancy curve fit. And I just want to emphasize that mathematically, what the big challenges are is how do you do this at massive scale? And for these nonlinear functions where there lives a multitude of local minima, right? But other than that, we're right back in those first few weeks of calculus where we learned many of these concepts. And that's the fundamental mathematical structure that sits around all of this.